Now we'll make things a little more complicated by adding a harmonic driving force to our damped oscillator. So as before, we'll start the restoring force, negative kx, due to a spring and Hooke's law, a damping force, a viscous damping force. Here I've drawn a piston pushing through some fluid to give negative r times the velocity. And now we add our driving force, F naught e to the I omega t. So F naught is the amplitude, and the real part of e to the I omega t will give us a cosine function. To get the differential equation, we use Newton's law again. Force equals mass times acceleration, and add up the forces, the restoring force, the damping force, and the driving force. Leaving just the driving force here on the right-hand side, we find that the sum of these terms here is now equal to the driving force, whereas previously it was equal to 0. So now we have an inhomogeneous differential equation instead of a homogeneous differential equation, as we had before. Just to remind you, the natural frequencies of the undriven system from the previous videos were gamma, the damping rate, R on M, omega naught squared rather, is K on M, and omega dash squared was given by omega naught squared minus gamma squared on 4. And these frequencies will come in our derivation as we work through it. So what happens? Before we solve this system analytically, I want to draw a picture of what happens so that we know where we're going. So using mathematical writers to do the simulation, this is time on the horizontal axis, the yellow line will be force, the blue line position. And this is what we see. What we see is the yellow line is a sinusoidal driving force. It's the same as we go through the simulation. At short times, what we see is the position of the oscillator looks kind of crazy. It seems to have two different frequencies going on here, and sort of double humps and kind of all kinds of stuff. It doesn't look sinusoidal at all. But as the simulation time increases, at long times over here, the position seems to be at the same frequency as the force, albeit 180 degrees out of phase. So we can identify two different regimes. This short time period here we call the transient regime, and at long time periods, this is called the steady state regime. What's happening here is at short times, we see behavior due to the natural response of the oscillator. So that is, we see this long frequency here, that's the frequency due to the natural dynamics of the oscillator, and this higher frequency term here, that's due to the driving. So what we see here is a mixture of the natural response, that is the solution of the homogeneous equation. That dies out, and you can see it dies out sort of exponentially because it's an underdamped oscillator. And then at long times, we do get the driven steady state response. So what we're going to do to find the steady state response is try a solution of the form a e to the I phi e to the I omega t. So that is at the same frequency as the drive, with some phase shift relative to the drive and some amplitude. So before we go on, I just want to be clear about what frequencies are important in our system. First frequency that's important is omega naught. Omega naught is the frequency of the undamped oscillator with mass m and spring constant k. This frequency is really important for both the response of the system to driving and also the transient behavior of the system. The second frequency that we have to consider is omega dashed. Now we found omega dashed as the resonant frequency when we include damping. So if there's some damping, it makes the resonant frequency a little bit smaller. Now a lot of the time we can ignore omega dashed. So we can approximate omega dashed is equal to omega naught, and a good rule of thumb is that this is a valid approximation if the ratio of omega naught to gamma is greater than about 10. That would make omega squared here about a factor of 400 bigger than this term here, and so this damping kind of goes away, and omega dash and omega naught are about the same. And then you can kind of simplify things and just don't have to really bother about omega dash at all. Just assume it's omega naught. That's okay. The third frequency we have is the driving frequency omega. So this is the applied force that we drive our system with. So bearing that in mind, before we get to the guts of a nasty looking calculation, I've got a content warning. So the following slides do contain a lot of maths. It's mostly complex numbers and square roots, so it can look a little bit ugly. There are some things we can keep in mind, however, to try and simplify our life as we work through this maths. First thing, when we're thinking about a driven oscillator, is there will be some transient behavior. when you first turn on your driving force, your mass will have an initial position and initial velocity. So that initial position and initial velocity will give some behavior to the system that will be going at the resonant frequency omega naught or omega dashed, and that behavior will die away for times greater than 1 divided by gamma, the damping rate. Even without the driving force, this transient behavior would exist because you give your system some initial position and velocity, you let it go, then it would decay. So that behavior is added to whatever we now find with the driving force added to that. But after this time sort of 1 on gamma, the transient behavior is not relevant anymore, and we can completely forget about it. So at long times, the system will oscillate at the driving frequency omega. We're driving at omega, then the position will be given by some sinusoid at frequency omega. The velocity will be given by some sinusoid at frequency omega. But the position and velocity will have a sinusoid that has some phase relative to the drive. So there's going to be a phase shift between the driving force and the position, a different phase shift between the driving force and velocity. The phase and amplitude of the position and velocity change quickly around the resonant frequency omega naught. And this is one of the most profound things about a driven system, is that as you scan the driving frequency, if you imagine you're starting at low driving frequencies and you increase the driving frequency when you reach the resonant frequency omega naught, assuming small damping, sorry, forgetting about omega dashed, as you reach that resonant frequency omega naught, you get a really huge change in the amplitude of the system, the position, amplitude of the position, and the velocity can become extremely large. Now, if we have some sinusoid that describes our driving force, we're going to have some sinusoid that describes the position and a different one that describes the velocity. If these two things are going at the same frequency, then all we need to do to convert the driving force into the position is multiply the driving force by some complex number. So here's our driving force F. It's got a frequency e to the I omega t, well, it's got a sinusoid e to the I omega t. The driving frequency is omega. The position has the same sinusoid e to the I omega t, but instead of having amplitude f naught, it's got some amplitude a times e to the I phi. So a will tell you how big the motion is. Phi will tell you the relative phase to the drive, because the drive has a phase term out the front here of a zero phase, so it'd be like e to the I times 0. Here we've got e to the I times phi, so there's a relative phase difference of phi between the force and the position. And this complex number e to the I phi will depend on everything: omega, omega naught, gamma, m, and f naught. The velocity we can find as a derivative. So we have this function for x, we take the derivative with respect to time, we get a factor of I omega out the front, and we can take this I and turn it into a I times pi on 2 up in the exponent. What that's telling us is there's always a pi on 2, a 90-degree phase shift between the position and the velocity. That's just a result of this harmonic motion thing, is that if you have a sine wave at the position, you can have a cosine wave in the velocity. Now what we have to do is find expressions for a and phi. Let's return now to our differential equation and see if we can solve it. The solution we're trying, remember, was x of p, a e to the I phi, e to the I omega t. We'll take this function for x and its first and second derivatives, and in the same sort of way as we did for the homogeneous equation, we'll substitute them into this equation and then see if we can find parameters that allow this to be a solution. In this case, we're looking for values of a and phi. So we substitute them in and we get this expression here. We can remove a factor of a e to the I phi, like this, and then divide through by this term in brackets, giving a e to the I phi equal to this function here. So this is a complex number, and this is also a complex number. We can write x of p, therefore, as a e to the I phi times e to the I omega t. So what we see here is this function for x of p oscillates at the driving frequency, omega, and has no free parameters. As an exercise, I'll let you show that phi can be expressed in terms of the parameters of the oscillator like this, and a, the amplitude of the response, can be expressed like this. One important thing we've got to realize here is that because the solution has no free parameters, it's not quite the total solution. The amplitude and phase here are fixed, but we know the complete solution of the differential equation must allow the fitting of initial conditions. So there has to be something more. But there is something more, because remember, we solved this homogeneous equation. That is, all this left-hand side equals 0. So whatever function x solves the homogeneous equation will evaluate to 0, which means we're free to add it to the solution we found on the last page to the inhomogeneous equation. The beauty is that the solution to the homogeneous equation includes two free parameters that we can fit to the initial position and initial velocity. Because remember, we had this solution to the homogeneous equation. For the underdamped case, there was a decaying exponential with time constant tau multiplied by these oscillating exponentials. The two free parameters for fitting the initial position and velocity are embedded in C1 and C1 star, these complex coefficients out the front here. I could equally write this as some number C, which is now a real number, with the decaying exponential and the real part of this oscillatory exponential and a phase shift delta. So the two free parameters now are the real number C and the phase shift delta. Normally we don't bother writing the function for the real part here, we just take that as being assumed. So in total then, the solution becomes the sum of the solution to the homogeneous equation and the solution we found to the inhomogeneous equation. So we have this part here that describes the response of the system in the steady state after it's been evolving for a long period of time, and this is the transient response that decays to 0 with some time constant tau. A mathematician would call this the particular integral, that's a steady state response, and the complementary function is a transient response that decays to 0. The useful thing to do at this point might be to compare the behavior of driven and undriven oscillators. So in this case we've got an overdamped oscillator, which would be like something moving through honey, and you can see you give it some initial position and the spring slowly pulls it back to equilibrium. If we were to drive this system, so we have exactly the same initial conditions, but now we add a driving, you see it starts off oscillating, but it's displaced from equilibrium, and after long times it's just oscillating around equilibrium at the driving frequency. For a critically damped system, it looks kind of similar. And for an underdamped system, now you have a natural frequency of oscillation, which is omega dashed. In this case, probably pretty close to omega naught. And then when you add the driving, you see you get some mixture of these two things. So at short times, it's pretty complicated. In this case, omega dashed is a lower frequency than the driving frequency omega. But it doesn't have to be that way. That's just this example. Another way of visualizing a damped driven oscillator is to look at something we call phase space. The top plot here is what we're sort of used to, where we have the position on the vertical axis and time on the horizontal axis. The bottom plot has the velocity on the vertical axis and the position on the horizontal axis. If we let these two graphs animate together, we see damped oscillations on the top graph as a function of time, as we expect. On the bottom graph, we see a spiral, and the reason for this is that the position and velocity are 90 degrees out of phase. And if you plot two things that are 90 degrees out of phase parametrically, like sine and cos, you get a circle, but the circles are getting smaller because of the damping, so we get a spiral. If we now look at the damped driven case on the right-hand side, then we see some quite complicated behavior, both for position as a function of time and in phase space. What we're seeing here is the transient behavior dying out. The transient behavior is this long period here, and eventually, for longer times, then all we're left with is the driven frequency, which is this high frequency behavior we see here. And what you see is this red dot going around in an ellipse in phase space, and we'll call this ellipse a limit cycle.